Welcome to the Skeptical Chemist YouTube channel, your online lecture hall where chemistry is made easy. Today we'll be talking about atomic mass and atomic weight. We'll start out with the background, why this concept is relevant in general to the discipline of chemistry, work through some definitions, and then, as always, dive into examples to really highlight these concepts. It is worth discussing why mass matters in chemistry. The short answer is that mass allows us to indirectly count atoms. Remember that chemical reactions occur between atoms, and reactions are governed by ratios of numbers. Because of this, it is possible to predict how much product will form in a chemical reaction if the amount of the reactants are known. In other words, chemists want to know how many atoms are present initially so they can predict the outcome of the reaction. Although the number of atoms in a sample cannot be directly measured, the mass or the weight of a sample is proportional to the number of atoms it contains. Therefore, by measuring the mass, chemists can determine the number of atoms in a sample. In this way, mass is fundamental to chemistry. Isotopes present a problem in terms of mass. By definition, isotopes have different masses. They also exist in nature in unequal distributions. For example, in a natural sample of carbon, about 99% is carbon-12, roughly 1% is carbon-13, and carbon-14 is present in trace amounts. If we wanted to use carbon's mass to predict reaction outcomes, we need a way to accurately represent the mass of all isotopes in the sample. Today, we'll cover how to do that. Before we dive into examples, let us define atomic mass and atomic weight. Atomic mass is the mass of a specific atom or isotope, and it is fixed and unique for that specific atom or isotope. For example, carbon has multiple isotopes, two of which are carbon-12 and carbon-13. Carbon-12 has a distinct mass, as does carbon-13. Similarly, uranium has multiple isotopes, and each isotope is associated with a specific mass. The atomic mass of an atom is determined by comparing its mass to the mass of a carbon-12 atom, or more accurately, by comparing its mass to 1/12 of a carbon atom. Let me explain. Carbon is the standard. It is a reference point. A carbon-12 atom has an atomic mass of exactly 12 daltons. 1 dalton is 1/12 the mass of a carbon-12 atom. And you may be thinking, this is a bit complicated for a standard that was chosen. By making 1 dalton equal 1/12 the mass of a carbon-12 atom, we get convenient near-whole number atomic masses. So for example, hydrogen has an atomic mass of roughly 1 dalton, oxygen has an atomic mass of roughly 16 daltons, and so on and so forth. Atomic weights roughly match the mass number. Remember, that's the number of protons plus neutrons, which is easier to work with. Now, the actual atomic masses deviate slightly from the whole numbers, and that's a conversation for a different day. A few technical notes regarding units associated with atomic mass are in order. The accepted SI-related units for atomic mass is the dalton, represented by dA. It's also called Unified Atomic Mass Unit, or U. Historically, the atomic mass unit was also used, but it is now deprecated. In 1961, IUPAC, or the International Union of Pure and Applied Chemistry, which handles chemistry-specific standards, like atomic weights, adopted the Unified Atomic Mass Unit, defining it as 1/12 the mass of a carbon-12 atom. In 1993, BIPM, or the International Bureau of Weights and Measures, which is located in France and is responsible for maintaining the international system of units, formally recognized the dalton as an accepted non-SI unit for atomic and molecular masses, and confirmed that the unified atomic mass and dalton are terms for the same unit. Now, the term AMU was deprecated because before 1961, chemists and physicists used different oxygen-based reference scales. A new term allowed them to redefine the reference scale and provide a consistent definition. I will be using dalton for the units of atomic mass, but if you see AMU, you now understand why this was used and why it's no longer used. The atomic weight is the weighted average of the atomic masses. Note that some textbooks refer to this as the average mass or the standard atomic weight, but atomic mass and atomic weight are two distinct terms with separate meanings. The atomic weight is a type of average that accounts for the different isotopes and the percent abundance, or the natural abundance, of those isotopes. Natural abundance is the percentage of a particular isotope present in a naturally occurring sample of an element on Earth. The isotopes of a given element are not equally distributed, or they exist in unequal quantities where some isotopes are naturally more abundant. Remember, we need to calculate an average mass of each element for calculations. And to account for the isotopes and their uneven distribution when calculating this average mass, or what we call the atomic weight of an element, the following equation is used. For each of the isotopes in a given element, the mass of the isotope is multiplied by its fractional abundance, and the sum of the products is taken. Multiplying the mass by the fractional abundance is what makes this a weighted average, and we will explain this in more detail in the next slide. Now, the total fractional abundance of the isotope has to equal 1. The fractional abundance is the natural abundance in decimal form and accounts for all the isotopes of that element. For example, if an element has two isotopes, one making up 75% or 0.75, and the other making up 25% or 0.25, the total fractional abundance must equal 1 because there are no other isotopes to account for. I find it helpful to use a numerical example with no chemical information to explain standard averages and weighted averages. This gives a more intuitive understanding of the mathematical definition of atomic weight, and we will do that now. Let us first recall the standard average. The expanded form of the equation shows that the average is the sum of the x values over the total x values n. A standard average can also be represented in sigma notation, where again it is the sum of the x values over the total number of x values n. Now, suppose we want to calculate the average of 10, 20, and 30. Here, 10, 20, and 30 are the x values, and the total number of x values is n, and in this case 3. The standard average is the sum of all the x values, so 10 plus 20 plus 30, which equals 60, divided by n, or 3. In this case, the standard average is 20. Now, if we want to place more importance on certain values in a data set, a weighted average could be used. And this is the equation for the weighted average. Here, each x value is multiplied by its respective weighted factor, and the sum of these products is taken and then divided by the sum of all the weights. So now say we want to know the weighted average of 10, 20, and 30, where the weights are 1, 2, and 3 respectively. So to do this, we multiply each x value by its weight. So 10 multiplied by 1, 20 multiplied by 2, 30 multiplied by 3. And the sum of these products, which in this case is 40, is divided by the sum of the total weights. 1 plus 2 plus 3 is 6. And so in this case, the weighted average is 23.3. Because we gave more weight to larger values, the weighted average is larger than the standard average. Now, in terms of the atomic weight, the fractional abundance of each isotope acts as the weight. If an isotope has a larger or smaller fractional abundance, the weight will make sure it is appropriately accounted for in the weighted average. Now let's work through some chemical examples. Say we're given this question. Silver has two naturally occurring isotopes. What is the atomic weight of silver? First thing to do is take note of the information that we've been provided with the question. We've been given the two isotopes, silver 109 and silver 107, the atomic mass of each isotope, and the percent abundance of each isotope. So the first thing that we should do is convert percentages to decimals so that we can work with it in the weighted average equation. Silver 107 has a percent abundance of 51.84%. We convert that into decimal form by dividing by 100, which gives us 0.5184. Silver 109 has a natural abundance of 48.16%. We convert that into fractional form by dividing by 100, which gives us 0.4816. Now we can use the weighted average equation to find the atomic mass. Remember, the equation says that for each isotope, we multiply the mass of the isotope by the fractional abundance of the isotope. I can simplify this in notation terms by designating mass M and fractional abundance F. Now I can start adding the information that I need. I take the first isotope, which is silver 107. I multiply the mass of the first isotope, silver 107, by the fractional abundance of the first isotope, silver 107. And then I add that to the mass of the second isotope, which is silver 109, multiplied by the fractional abundance of the second isotope, silver 109. And now I can start adding the numerical values. The mass of silver 107 is given in the table, so I can add that in. The fractional abundance of silver 107, we just converted, so I can add that in. And then I'm going to do the same thing for the second isotope, silver 109. The mass, which is given in the table, by the fractional abundance, which we calculated above. I multiply these terms through to get numerical values, which is 55.418 plus 52.448. I add those together, and the result is 107.87 daltons. If you check with the periodic table, that is the atomic weight of silver. Now say we're given the following question. Chlorine has two naturally occurring isotopes. What is the atomic weight of chlorine? Again, the first thing that we do is take note of the information we've been given. We've been given the two isotopes, chlorine-37 and chlorine-35, and their atomic masses respectively, as well as their percent abundance. First thing that we're going to do is convert the percentages to decimals. Chlorine-35 has a percent abundance, or natural abundance, of 75.76%. Divide that by 100 to get 0.7576. Chlorine-37 has a percent abundance of 24.24%, which we divide by 100 to get 0.2424. So these are in decimal form. Now we use the weighted average equation. Isotope 1, or chlorine-35, we want to take the mass of that, multiply the fractional abundance of isotope 1, chlorine-35. Then we're going to add that to the mass of isotope 2, chlorine-37, multiplied by the fractional abundance of isotope 2, chlorine-37. Now we're ready to start adding numerical values. The mass of chlorine-35 is 34.969, which is given in the table above, and the fractional abundance is 0.7576. We got that from taking the percent abundance given and converting it into fractional form. The mass of the second isotope, chlorine-37, is 36.966, given in the table above, and the fractional abundance of chlorine-37 is 24.24%. Is 0.2424, which we got by taking the percent abundance and converting it into fractional form. When we calculate these numerical values, we get a value of 26.4925 plus 8.9605. The result is 35.45, which will be the atomic weight of chlorine. Now, I do want to just take a second and compare this average weight to a standard weight. If we were to take the masses of the two isotopes, chlorine-35 and 37, sum them and then divide them by 2 to get a standard average, we're around 0.5 daltons off. Now this may not seem like a lot initially, but when you start doing calculations in stoichiometry, it matters. So I just want to highlight the difference that if you use the weighted average versus a standard average, you will get different values. It's also interesting to compare the two examples, or the results of the two examples we just went through. So we calculated the atomic mass of silver and chlorine. Now silver has two isotopes, and the masses of those two isotopes are pretty similar, and the percent abundance is pretty similar. You can see that in the weighted average, the result is essentially a numerical value in between these two isotopes, which makes sense. Now chlorine has two isotopes, but one of the isotopes is quite a bit, in terms of abundance, is more abundant, 75 compared to the 24.24. And so you see that when you compare the weighted average is 35.45, which is closer to this chlorine-35 than the chlorine-37. Quickly, I want to go through two kind of unusual examples that maybe you won't see in a homework problem or on an exam, but still they're worth looking at. Cobalt is a monoisotopic element, meaning it only has one isotope. And so if we calculate the atomic weight of cobalt, we can go through the same steps, but because it's the only isotope, we're going to wind up with the atomic weight being equal to the atomic mass. So if we convert percent abundance into decimals, 100% is converted into decimal form of 1. We use the same weighted equation, the mass times the abundance. And here, because we only have cobalt, we take the mass given in the table of cobalt, 58.993, multiply by its fractional abundance, 1. And we come to the weighted average is the same as the atomic mass. The second example that you may not be forced to work through by your professor is an example of an element with more than 2 or 3 isotopes. So for the example that I chose to pull is 10, but there are multiple examples of this. And say you did want to find the atomic weight of 10. You're going to go through the same steps that we did before. You're going to take the percent abundance, convert it into decimal form, and then use the same weighted equation that we've been using, which is for each isotope in the element, you take that isotope's mass times its percent abundance in fractional form, and then eventually sum these terms. So I've written out the numerical values here. Obviously, we won't go through step by step because you should be comfortable and know how to do that now. But I do want to do one more analysis point, which is that the atomic weight of 10 is 118.61 daltons, and that is going to be closest to the atomic masses of 10, 118, and 120, who have the highest abundance. Now let's work through an example, which is a popular problem type to ask on homework questions and exams. Suppose you are given the following question. Boron has 2 naturally occurring isotopes, boron 10 and boron 11. Using the relative atomic mass of boron and the isotopic masses, determine the percent abundance of each isotope. In this question, the term relative atomic mass is used, and this is a synonym for atomic weight. The same equation that we've been using to find atomic weight will be used to find the relative atomic mass. The question also uses isotopic masses as opposed to atomic masses. This is also a synonym. Chemists often use isotopic masses when talking about isotopes specifically. Now let's start by using the atomic weight equation as a kind of roadmap to see what information we need or what we need to do. We know that we have the atomic weight, or the relative atomic mass of boron. The atomic weight is what is given on the periodic table. We also know that we've been given the atomic masses of both isotopes of boron. So we need the percent or the fractional abundance of each isotope. But now we know that we can solve this algebraically for both percent abundances. And note here, if the question gave us one of the 2% abundances and asked to solve for the other, so we'd have a numerical value for one, it would be pretty straightforward. We'd only need to solve for one variable. But we want to solve for both percent abundances or both fractional abundances, so we need to assign a variable to both the fractional abundance of B10 and the fractional abundance of B11. We know that the fractional abundance of both isotopes has to equal 1, so we can let the fractional abundance of B10 equal x, and the fractional abundance of B11 equal 1 subtract x. This works because both abundances equal 1. If the fractional abundance is not B10, then it has to be the fractional abundance of B11. That is, if it's not x, it is 1 subtract x. Now, this is just an algebraic equation that we can solve. First, let's replace our formal notation with x and x subtract 1, just so it's easier to work with. Now we can simplify the right-hand side of the equation by distributing 11.009 into both terms in the parentheses. We combine like terms by subtracting 11.009 from both sides of the equation. We'll wind up with this. We can further simplify the right-hand side of the equation by combining like terms. So we'll subtract 11.009x from 10.013x. And now we can solve for x by dividing both sides of the equation by negative 0.996, which will leave us with x equals 0.1987. And I cut it off at 4 decimal places here. So we set x to be the fractional abundance of B10, and 1 subtract x to be the fractional abundance of B11. So 1 subtract 0.1987 equals to 0.8013, which is the fractional abundance of B11. And the question technically asks for the percent abundances. So to convert to percent forms, we just multiply each by 100. These values are very close to the values reported for boron isotopes by the IUPAC technical report. To get more precise results, we would have to use the full 6 decimals reported in the isotopic masses by the IUPAC report. And I chose to use less decimal places to make it easier to follow. If you are asked to solve for the percent abundance or the fractional abundance of an element with 3 isotopes, and all 3 fractional abundances are unknown, this won't work. Let's use neon as an example. Say you set up the variables in a similar manner to what we did before. You let x equal the fractional abundance of neon 20, x subtract 1 equal the fractional abundance of neon 21, and y equal the fractional abundance of neon 22. Because the fractional abundances must sum to 1, we have the first equation. We also know the atomic weight equation. So what we have here is 2 equations and 3 unknowns, and therefore there are infinitely many solutions. To get a unique solution, you must be given one of the 3 abundances. Watch out for these types of questions in multiple choice tests. If you enjoyed or learned anything from this lecture, hit like and subscribe. Thanks for watching.